Hi, I'm Nick Wazinski, and I started my research for this project with the paper by Huan Wang, Synthesis of Aligned Carbon Nanotubes on Double-Sided Metallic Substrate by Chemical Vapor Deposition. Before we get into exactly what this is, let's take a look at carbon nanotubes in general. The dictionary definition of a carbon nanotube is a fullerene, having a cylindrical, toroidal configuration. All a fullerene is a group of carbon molecules. Carbon nanotubes are also defined as allotropes of carbon with a nanostructure. Another example of an allotrope is diamond. Some terminology used in the discussion of nanotubes is the SWNT, or the single-walled nanotube. Another type of nanotube is the MWNT, or the multi-walled nanotube. The torus is a donut-shaped nanotube, which is used in magnets. Carbon nanotubes have tremendous capabilities. Their capabilities range from their tensile strength, their thermal conductivity, their electroconductivity, and their uses in kinetics and nanomachines. Let's start with their tensile strength. Carbon nanotubes have a specific strength of 48,000 kilonewton meters per kilogram. To put that in perspective, steel has a specific strength of 154 kilonewton meters per kilogram. Just how strong is that? A carbon nanotube cable with a cross-section of just 1 millimeter squared was tested to support 6,300 kilograms. Nanotubes can be used as both insulators and conductors. They conduct 6,000 watts per meter per Kelvin, while steel is only capable of conducting 385 watts per meter per degree Kelvin. Carbon nanotubes have potential in electric applications as well. Specially designed nanotubes can carry a charge density of up to 4 times 10 to the 9th amps per centimeter squared. This is about 1,000 times more than copper, which is considered one of our good conductors. Nanotubes can also be used in nanomachines. Carbon nanotubes placed inside one another have almost zero rotational friction. Nanotubes synthesized in a torus form have magnetic moments thousands of times greater than any material known on Earth. Now on to how nanotubes are formed. Nanotubes can be synthesized by either arc discharge, laser ablation, or chemical vapor deposition. The first way that carbon nanotubes can be synthesized is through arc discharge. This takes place when carbon nanotubes are produced when the carbon in a negative electrode sublimates in the intense heat. Although this is how carbon nanotubes were originally discovered, it only creates about a 30% yield, and carbon nanotubes about 50 micrometers long. Laser ablation is one of the most expensive ways to produce carbon nanotubes. In this method, a high-intensity laser vaporizes graphite. When the vapor condenses, nanotubes form. This produces mainly single-wall nanotubes. The radius of these nanotubes are controlled by the heat. The yield is about 70%, making it more practical. The last method to synthesize carbon nanotubes is chemical vapor deposition. Researchers in the University of Cincinnati created nanotubes up to 18 millimeters in length on a First Nano ET3000 carbon nanotube growth system. Chemical vapor deposition, or CVD, is the process most commonly used now on the commercial scale. A metal substrate, such as nickel, cobalt, or iron, is laid down and heated to approximately 700 degrees Fahrenheit. A carbon-rich gas, which will provide the carbon for the nanotubes, and a process gas are fed into the reactor. Nanotubes grow at the substrate of heated metal. The process of chemical vapor deposition is still being researched today. Huan Wang's method decreases growth time, allows for growth on both sides of a substrate, and can create carbon nanotube films for use in other applications. The applications for carbon nanotubes are seemingly endless. These include their structural applications, electromagnetic, electroacoustic, chemical, and mechanical. Some of the structural applications of carbon nanotubes are advanced water-resistant clothes and stronger body armor. They can be used to replace other metals in sports equipment, making things stronger and lighter. They can reinforce buildings and can be used in concrete to make them stronger and prevent cracking. They can be used in the cables and suspension bridges to make bigger bridges with lighter weight. One of the most famous uses for this is the space elevator. They also have insulating properties for fire containment and protection. Their electromagnetic capabilities include more efficient brushes and electronic motors due to their superior conducting capability. They can also be used as magnets in such motors when a multi-walled nanotube is formed in a torus shape. They have superconducting tendencies. They can also be used in light bulb filaments, solar cells, ultracapacitors, and much more. One of the most recent advances came in November 2008, when it was announced that a company had created loudspeakers from sheets of parallel carbon nanotubes, generating sound in a manner similar to how lightning produces thunder. In the chemical field, the carbon nanotube membrane formed by processes such as those discovered by Huan Wang can be used as filters to reduce emissions in power plants and also to filter water. They can be used to hold biological molecules and can provide high-pressure storage for hydrogen. Some of their mechanical applications include uses in frictionless nanomachines that are also slicker than Teflon, and on such membranes like those created by Huan Wang, liquid flows up to 5 orders of magnitude faster than predicted by classical fluid dynamics.